But anyway, it's about time, so let's kick this off. We have the keynote from guess who? Walter. Hey, take it away, Walter.
Okay. DMD consists of a compiler, an optimizer, and a code generator. And many people have thought they would contribute to the code generator, and they're put off by its complexity. Well, it's a difficult piece of code to master, and so by popular demand, I decided to do a talk on a brief tour of the code generator. If you want to learn about code generators, you're in for a lot of trouble because everybody writes books about lexing, fewer write books about parsing. It gets worse and worse until you wind up with 0 books on code generation. Now, who knows what's wrong with this slide? I made up all the numbers. But it's my general feeling with it that there's just no information out there on code generators. And so that's one reason why I kind of call it a black art. Okay, now you have to, when you see this slide, you have to imagine the wind whistling through the canyon and the hawk cry, which you will see on every single wilderness picture. You'll notice there are no roads in the code generator. So if you want to write a code generator, you got to rely on articles, papers, CPU's specifications. No, those are really fun reading. Dogged persistence helps a lot. I'm currently trying to learn the Arch64 instruction set, and dogged persistence is the only way I'm getting through it because it is baffling the way they wrote that spec. Godbolt is a wonderful, wonderful gift for exploring not how code generators work, but if you play with it, you start getting a sense of how it does work. And of course, you got to rely on yourself. Nobody's going to do it for you. This will be about DMD's code generator, which has a history going back to, I believe, 1981. I don't know if it's older than what GCC started with, but it's definitely a lot older than LLVM. I had no examples to go by and sort of invented my own scheme from nothing. It started as an 8088 16-bit code generator. The basic design has survived revolutions for the 286, the 386 32-bit code, 64-bit code, and now the Arch 64 architecture. So I think it's basically a sound design because it's adaptable to all these different machines. It's also booth licensed, which means anybody can use it for anything they want to. It'd be fun to see what someone can do with it. I know that the code generator is a confusing mass of code. However, the data structures it has in it are actually pretty simple because, when I designed it, I didn't really know anything about data structures, so I still don't. All I know are arrays, linked lists, and hash tables. It's the only data structures I use. But understanding the data structures is really kind of the key to victory in understanding how the code generator works. Expressions. How do we represent an expression? We do it as a binary tree. Does anybody find this confusing? Absolutely nobody. So you see, already we're making progress. Things are looking good. By the way, it takes me a lot less time to draw these diagrams by hand and scan them in than trying to figure out how to use those image editors, which are awful. So you get hand-drawn stuff. So imagine you're back in college and the prof is writing in chalk on the board. The compiler generates this intermediate code. And the expressions tree structure, and you'll see you have the discriminator, which is which operator node it is. And then the data type flags for various things. Ecount and ecomsub are for common subexpression tracking, which we'll get into later. And then it's a union of 3 things, because you can represent 3 things in the element tree: a constant, a variable, or another tree. And also the trees can be binary or unary. So that looks simple enough, right? Anybody can figure that out. And the compiler offers you some aids to figuring it out. Let's start with our useless function called horse. I always have trouble coming up with new names for functions. I really get tired of foo and bar. And if you compile with the --b switch, it'll show you the trees that it generated in a human-readable form, well, just as expressions, algebraic expressions. And if you compile with another switch too, you actually get a more complete dump of the data structures. These are kind of invaluable for figuring out baffling things about your code. Has anybody heard of a single assignment intermediate code? A couple people, actually quite a few. I heard all this hoopla about single assignment stuff, and then I kind of had an epiphany that a binary tree is exactly the same thing. The single assignment is implied, it's the result of the tree. That invariant is held in this. A element has one and only one value to it. So it's a single assignment. And I've been told that you can't do single assignment optimizations with the binary tree, which I did anyway because it's the same thing. I can't tell you how many times I've been told that I can't do things with that old code generator, and it's turned out to not be true. But we have control structures, go-tos, if-else, switch statements, loops, things like that. So how do we model that? We have a linked list of blocks, and these are called basic blocks in the compiler terminology, and it's a linked list of elements, or those tree nodes. First is the discriminant, and you have different kinds of blocks, and you have a go-to block, which goes to another block, obviously, and if true, it goes to another block. RET means it returns, and return EXP means it returns an expression. The successor list are the next blocks to execute, which is distinct from the next block in the function. For example, if you have a sequence of statements that ends in a go-to and code after it, the code after it is not where the go-to is going to, so you need two things. One is the successors. Like a switch statement will have successors that consist of all the cases and the default. And a go-to will have a single successor, a return will have no successors. And the next is the next block in the list, and when it's null, that's the end of the function. So I thought I would actually use a real example for once, a function that actually did something useful. So pop count, everybody knows what pop count does, right? Counts the number of set bits in an integer. And so you can see what it looks like in the source code, and on the right, what it looks like in the intermediate code. You have the 5 blocks, the go-to, the if statement turns into an if true, a go-to goes to the next statement, which goes back up to the beginning of the loop. The BC true up there has 2 successors. One is the loop body, and the other one is what happens after the end of the loop. Interesting, there are no high-level constructs here. It all consists of go-tos. Some code generators work by trying to generate code for while loops and things like that. This one does not. Everything's broken down into Fortran style, or actually basic style, go-tos and conditionals. It makes it a lot simpler to reason about when it's written that way or converted into that. The code structure is a linked list of instructions. One of these is allocated for each instruction that is generated, and you have the next one, which is, of course, the next instruction, and null when it's at the end of the list of instructions. You have a bunch of flags for various things, and then you have IOP as the operator, and that's the binary of the instruction. That's the opcode. LEA, which is the addressing mode, which is kind of a bit specific to the x86. It has an EA and an addressing mode there. And then since the x86 has 2 operands, there are two more discriminated unions in there, one for the one operand and the second one for the second operand. And the opcode tells you which of those contain valid information and what it is. There are a few other bookkeeping things added onto this, but this is the basic way it works. So here's our pop count function, and we see that the instructions generated match the block structure I showed and the expression trees that I showed, with the addition of a function prologue and a function epilogue. The prologue is when your function is entered, it has to set up the stack frame for it, and the epilogue tears down the stack frame. Also, one thing the prologue does, though it doesn't need it in this function, is to save registers that need to be saved, and in the epilogue it restores them. If you compare this with the block structure, you'll see a very good correspondence with the high-level code and the generated instructions. And if you look at this for a while, it will start to make a lot of sense. It turns out that even without the optimizer running, there's some optimizations that are cheap to do and really easy to do. And one of them, I call them local optimizations, and they're in the file cglm.d. If it starts with the code on the left, it transforms it into code on the right. And the reason for that is it can be evaluated with one less register. Because the one on the left, you have to compute the left expression, a plus b, and then you need to save its result in a register. And then you got to compute the right, c plus d, and put that in a register. So now you've consumed two registers to evaluate this expression. Whereas if you rewrite it in the form on the right, you only need one register to evaluate it. So this is kind of a critical optimization, and it's especially useful on a CPU like the x86 that has a really small number of registers, like 6. Common subexpressions. You think, why aren't common subexpressions left to the global data flow analysis optimizer? And the reason is because if you don't do simple common subexpressions, there's an explosion of code generated by the compiler. Even in the unoptimized, just generate the code thing, it still does common subexpressions because it's an extremely effective way to reduce the number of instructions required to generate it. And how it works in this is you see in the expression, 2 times b is repeated twice. And since b is not modified in between those computations, it's a common subexpression and does not need to be modified twice. What happens is the code snips off the second one, and that ... line points to the first one. And if you'll recall, there was an ecount and ecoms field in the code data structure, and when those are non-zero, that means it's a common subexpression. Ecount gives the number of uses of that expression minus 1.
How do you identify the common subexpressions? Do you keep a hash table or?
The question is, and it's a great one, is how do you identify the common subexpressions? What you do is for each basic block, you walk the tree, and anytime a value is computed, you put it on a stack or in an array. You also enter it in a hash table. And whenever you modify a variable, you go back through the array and delete everything that depends on that value. And the cgcs.d is the module that does that. So that's how it works. It's the only complexity in it is the large number of operator nodes. The operation of it is very simple. That's another reason. It's simple and also very fast to do this. So that's why it's in the default compile.
What is the complexity of the method you just described? Is it linear with the number of nodes? Because I've been thinking about these things previously, and I've come to the conclusion that we should kind of create hashes of trees, subtrees, and if you store that in a hash table, and then you can very quickly find similarities between code. And
You're absolutely right, and that's exactly what it does. The trees are all hashed and put in the table, and so you can quickly look up to see if something's already in the table, and every new one you generate, you put it in the table.
I should have got you a little bit earlier, Walter, but you were talking about SSA and the trees.
Yes.
And now you're going into optimizations using the trees. And for those that are interested, you can get a pretty good scan of the possibilities if you query Grok on this. The optimization benefits of trees versus SSA, and it gives 10 different things, which I just scanned. And my knowledge is a little dated at back ends. I worked on things in the 70s, so it's a while. But currently, Grok indicates there are at least 10 different types of optimizations where SSA has some benefits. So you might want to query that if you're concerned about the trees versus SSA type of things, particularly the question about what's the complexity. That's what triggered it.
I've thought many times about changing it to SSA, and I just could never find a reason to.
Maybe you're on X. Give Grok a shot. See what you think.
All right, good idea. Register mass. You know, the x86, like I said, had 6 registers. Well, actually it has 8, but one of them is the frame pointer and one of them is the stack pointer, which are not really amenable to general purpose. So you got 6 registers, and how do you deal with them efficiently? You use a register mask. The back end has a number of symbols which are used to keep track of registers for various purposes, and it does it with a mask. When I first looked at the ARCH64 instruction set, I panicked because it has hundreds of registers. Oh crap! You know, my whole design is going to fall to pieces. But then I noticed something interesting: is it really only has 32 registers. There's 32 registers, then there's 32 floating point registers, and then all the SIMD registers are mapped on top of the floating point registers. So I dodged a bullet on that one. But still, I decided to keep track of the floating point registers and their SIMD overlays separately. So that means I have 64 registers to deal with, which fits nicely into the ULOM. So as part of the ARCH64 thing, I upgraded the register mask to 64 bits. Unfortunately, some of those registers aren't available. They're used for special purposes. I finally found a specification on exactly what registers are used for what. So there's only a subset of registers available to the code generator, and that goes into the global called all regs, which is all the integer registers you can use. And then you have FP regs, which is the mask of the floating point registers you can use. On the x86, you have the XMM regs, which are the SIMD registers, mfunc reg, which is the registers preserved by a function, and msave reg is the registers we'd like to save. A lot of the operations in the code generator boils down to bit masking operations. And I'll get more into that a little later, but once this is clear what these variables are actually for, it's what drives code generation. One thing the x86 has is it has something called an effective address, which is a single byte, and it's sometimes 2 bytes because nothing is very consistent in the x86, but it encodes 3 kinds of addresses. There's the offset, and by offset I mean 0 to 32 bits or 0 to 64 bits. So it's basically any address on the machine. And then you have another effective address, which is the offset plus the value in a base register, or you have an offset plus a base register plus an index that is scaled by 1, 2, 4, or 8. So the instruction set for the x86 is all kind of oriented around the EA, and weirdly the ARCH64 is not. Which caused me a significant amount of grief, and I had a couple moments of panic thinking the whole code generator is designed around the EA, and the ARCH64 does not have EAs. What am I going to do? And it really took me about 2 weeks to figure out a different way of doing that. But anyhow, it was one thing that I was a bit blindsided on, because I just assumed, of course, it'll have addressing modes. Well, it doesn't actually have addressing modes. not in any reliable fashion. The entry point for the code generator. That's the first thing you got to find when you're looking at how DMD code generator works is where the hell is the entry point? It's not really very clear where it is. Well, that's where it is. You generate code function by function, not module by module, not program by program. It's all based around functions. It generates code for one function at a time. What that write func does, first it sets up the symbol table. And the symbol table is a symbol table of local symbols, which include the parameters. It optionally runs the global data flow analysis optimizer. So that's the entry point for the optimizer. Then it calls CodeGen to generate code for it. Shuts down the data structures, emits debug info for the function, and optionally saves the result for possible inlining later. Which means, of course, you can only inline a function if it's already had the code generated for it. Works great for C and C++ because they're order dependent, but D is not order dependent, so this causes a little bit of a problem with D. So what the code generator does is, sets the stage, initializing variables. If the optimizer runs, it does things in a loop, because it turns out in advance, you cannot tell what registers are going to be available to put to assign variables in the registers. And the only way you'll find out is if you run the code generator. Well, so now what do you do? Your only option is to do it iteratively. So how it works when the optimizer's on is it generates code as if none of the registers can be used, or that nothing can be assigned to a register. And then it looks to see what registers weren't used, and then assigns those variables to those registers, and it runs it again. And it does this in a loop until it's no longer able to assign any more registers. For a non-trivial function, it can usually run through 5 or 6 times generating code for it before it converges on a solution. And the way it's set up, it's guaranteed to converge on a solution. Not necessarily the optimal solution, but at least it's not going to loop forever. Although there have been bugs where it would loop forever, but those were bugs. But the unoptimized code is it just loops through the blocks in the order that the blocks appear and generates code. The only register assignment it does, once it runs through once, it looks to see if any registers were not used, and then it will just change those variables to using the register, but it doesn't rerun the code generator to look for more opportunities. It only does it once. It's a very simplistic one.
This incremental algorithm, is there a name for it? And if so, if there are references to this in the book, or did you come up with it on your own?
It's the only thing I could think of. Okay. Oh, the question was, did I think of this on my own? And yes, I did, because I didn't have anything to go by. Like I said, I've never found a book on code generators.
Could you clarify an example about this algorithm? What does it mean, whether or not a register can be allocated, and how that relates to optimization? Maybe an example would help clarify.
All right, I do have a slide coming up on that, but the slide isn't actually very good. Remember I said bit mass, okay? So every block has a bit mask, one of those register bit mass on it. And whenever a register is used in that block, it sets that bit to 1. So now when I'm generating code, I have a whole bunch of bit masks. And then I have my variable. So that is a bunch of bit masks like this. And then I have my variable, which is bit masked like this. And I go, it fits. So it's extremely efficient, actually. Works very well. I did not invent that. So I just heard about it. It's basically coloring. Continuing on with what the code generator does next, is it's still not done. After it's generating code for the function, it turns out that some variables are never used. And the only way to detect that is to try generating code and see if it's ever used. Well, it marks a variable as I've used this. And then when it's allocating them on the stack, it doesn't need to allocate space for a variable never used. Another thing it can do is, there's a thing called a live range. Does everybody know what a live range is? Okay, live range is inside of a block is a variable used. And even if the variable isn't used in a block, if you have a block that sets it, a block that does something else, a block that reads it, the variable is still live in this block in between. So once you've computed that, you can take two variables, and if their live ranges do not intersect, you can map them into the same memory location, which plays hell with your debugger, but who cares about symbolic debugging anyway? Yeah, you know what I'm talking about. The problem with symbolic debugging of optimized code is the classic problem of trying to turn hamburger back into a cow. It doesn't work. It will never work. IBM published papers trying to do it, and nobody has ever figured it out. The only way you're going to make symbolic debugging work is if you don't optimize the code, because by the time the optimizer gets done with it, it's just a hash. And then generates the function prologue and epilogue, which you saw in the previous slide. Again, you don't know how much stack you're going to use. You have no idea how much stack you got to allocate. So you can't generate the prologue and epilogue until you're finished generating code. In the generated code, you also wind up assigning addresses because you can finally figure out how big your instructions are, because there are multiple variants of each instruction and they vary in size. So until you finish the code generator, you don't know where these instructions are. And so now you can assign addresses, and you have to do that iteratively too, because once you shrink the code, it may open up more opportunities for shrinking the code further. If you're familiar with how the branch instructions work for the x86, there are various sizes of them. Anybody heard of peephole optimizations? Peephole optimization is you have two instructions, one after the other, and a different part of the code generator generated one instruction, then generated the other. But if you look at the two together, they can be combined into one instruction. That's called a peephole thing. But my code generator works a little different. It has what I call a pinhole optimization. Stupid name, I know. But what that does is a lot of the instructions have a shorter form of them on the x86. So what this goes through, and any instructions for which a shorter form is available, it will replace the longer version with a shorter version. And this relieves some of the complexity of the code generator because it generates the more general instructions. Then the pinhole optimizer goes through and tries to replace them with simpler instructions. Optimize jumps. Jumps to jumps, you can skip the intermediate jump. And that again can expose more opportunities for shrinking the code, so that's done iteratively too. Once you're all done with that, you can generate the switch tables because now you know where they go. And lastly, you emit the generated code. How the code is generated is it's all driven by the operators. So it runs through the blocks, and then it generates code for a block, which looks at the tree, looks at the operator, and there's the function associated with each node that is then called to generate code for that operator. And there's a couple of hundred of those. I just picked the beginning of the table so you kind of get the idea. They all follow the same pattern. Okay, element nodes. And constant result of an element node, the address of an L value. And I know I covered this before, but one additional one is the common subexpression. The purpose of ecount and esub is to be able to tell if I need to generate a common subexpression, reuse an existing common subexpression, or I'm done with that node. So that's why I need two counters. So it works a lot like reference counting. Reference count and memory allocation. And if you're comfortable with that, this will make a lot of sense to you. L values only come in two varieties. You either have a variable or an indirection. This is the simplest code generation function I could find in the compiler. And it actually fits on two slides, which I'm rather amazed. The arguments are CG state, which is the global state of the code generator. The next one is the code builder, and the code builder is a sink for generated instructions. this code used to manage the linked list all by itself, which turned a fair amount of complexity, and I managed to push it all out into a sink. And then you have the element node that you want to generate code for. People have complained about the use of E as the variable name as the backend. Well, it turns out that I think every single use of E as the variable name in the backend, it's always as an elem, an instance of an elem. And the variable C is almost always an instance of an instruction. So it's not completely crazy. And then you have this thing called a reference to regMT is the register mask and p return regs. And this is a very crucial piece of information. P return regs, you go into it with a mask of registers that I want the result to be in. Okay? Oftentimes there's a list of registers which will work fine to get the result in, or there may be a single bit set in it saying I have to have the register or the result in this register. And there's another bit in there for the flags saying I want the result in the flags, which also influences how the code generates. Since it's a ref variable, it's updated, and what it's updated to is where it actually wound up. So here's the typical flow inside of a code generator function. It extracts the types. The rex is one of those weird problems with x86. Possible regs are regs I need to use to evaluate it. Down there you see cod elem that evaluates the left tree into return regs. And then you mark those registers as destroyed because I'm going to destroy them. And then you generate the instruction, which is a not. If it needs two registers, there's two nots being generated. And the last thing is the fixed result, which takes the values returned in return registers and then bashes them into fit into the desired p return regs. Okay, this is a rehash of the register allocation scheme. I think we already talked about that. Finishing things up, we write the code bytes to a buffer, write the fix-ups, write the object code to a file. There are currently 4 completely different object files with completely different fix-ups. Fix-up is something the compiler cannot know until link time. So it emits a fix-up record, which the linker reads in order to make the adjustment to where things actually wind up. They tend to be confusing and extremely poorly documented. So there are always a lot of detailed splunking work to figure them out. Inherent limitations of this code generator. The high bytes of the registers are not independent registers and cannot be used that way. No more registers than fit in 64 bits. Cannot have loops inside of an expression tree. A limitation, not that severe though. x87 is a giant kludge because it doesn't have registers as a stack machine. Why is it so complicated? A microcomputer has maybe 40 instructions, and modern CPUs have well over 2,000 instructions with multiple variations on those. So there are multiple ways to load a constant into a variable, which adds to the complexity because in each situation you want to pick the optimal way to load a constant into a variable. Code generator is never finished. It's an endless employment opportunity because the CPUs are constantly changing, but this presentation's finished. So, thank you. So, time for questions.
I've been thinking about your presentation, and I'm pretty sure the tree format you showed at the beginning really is just static single assignment in a head. If you ignore the fact that it's technically in the form of a tree and think about it, the tree nodes as instead of addresses as variable names, then it's pretty much looks like I remember LLVM SSA looking. Okay.
Yeah, that was my impression too, although I've never looked at LLVM. I just heard it was SSA. SSA is covered in a lot of compiler books on optimizations.
One question about the documentation of backend. Actually, this presentation is very intuitive in terms of what the backend do, and a lot of people don't actually know what are the steps, and you actually documented a lot of the things. Is it something that you really want to expand? Documenting like how, for example, a particular code gen part is doing in terms of implementation?
Well, I do try to document it, but apparently not well enough because everyone who's tried it has given up on it. So I definitely could use improvement.
Including myself.
Yeah, I do apologize for that.
But as part of your ARH 64 change, did you manage to understand like some part that maybe you forgot? But
oh, well, that's a great point because parts of the code generator I haven't worked on in many years, and I found that I had no idea what it was doing, so I had to relearn it, which actually turned out good for this presentation because I had to relearn how the code generator works, which kind of gave me a humiliating moment that I didn't understand some of the code, and I had to
it's a good time to document it.
What?
It's a good time to document it.
It's better.
Okay, cool.
Like I said, it's so blasted complicated, not because the code generator is complicated, but because the instruction set is complicated. I mean, the number of different move instructions on the ARCH64 is kind of insane. And they all have the pseudo-op of move, but they're all very different bit patterns and different uses.
This is from B2Temp on YouTube. What is the state of the back-end inliner? Is it finally enabled, or is it still the front-end one?
The back-end inliner is enabled. It's running. But I never got around to replacing the front-end one with it. One of its difficulties is, as I said, it can only inline a function that's already had the code generator generated for it. So until I take that step, it's going to be less than it could be, shall we say?
What is the publishing date of your book about code generation?
Well, one of the things that stops me is nobody ever made money writing a book about compilers. Well, at least we got something now. We got a presentation. We can add that as the documentation link in the code generator files. I know you're not going to get much out of a 40-minute presentation on a code generator. It's something that you got to spend a lot of time with. The best I could do is just kind of, hand wave where this is and where that is on it.
What I don't understand is when you compile, I understand that then you can generate the code. But if you have meta programming and compile time execution, how do we actually do this in a linker? I don't understand.
How do you compile in the link?
Yeah, well, how does a linker do this?
There are different schemes for doing that, but usually you got to put a compiler in the linker.
Okay, so it's actually because we actually just feed all the code into the compiler now. I don't know if that's better.
Yes. DMD is designed so you can hand it all the code for your project and it will build everything, but it doesn't actually generate an executable. It still relies on the linker to do that. And there's also the D runtime library it links in. It doesn't compile it in, so you still need a linker. I've thought many times about actually integrating the linker in with a compiler so they aren't separate programs. So the compiler could generate a executable directly. What's always stopped me is the linker is a very simple program, except the people who wrote them made them absurdly complicated, which is an unforgivable sin, but what can I do? If you want to look at simple ones, look at the ones for the 8086. The linkers were very simple on those, but somewhere, the whole business went off the deep end, and I don't know. I don't even want to touch them. They're so complicated now.
If you would start writing the same code generator now, and back in the days, x86 16-bit was basically the only thing around, and now you have ARM and RISC-V, and it seems like a lot of the code generation was written specifically for 16-bit x86 or x86 in general. What would you do different if you would start now?
I've often been frustrated by the block structure and the expression elements. You can't have loops in them. I'd find a way to deal with that probably. But been pleasantly surprised at how amenable the code generator is towards modern optimization techniques. And people told me I couldn't do a structured assignment of aggregates, the SOA. I thought, I looked at what SOA was, and I forgot, is that the right acronym, Timon? Structured, it takes a struct, like of int A, int B, int C, and actually divides it into 3 variables that are optimized and generated code and optimized independently. And I looked at that, I thought, there's no reason it can't do that, and it could do that. I was told it couldn't do various other loop optimizations. Well, it does all the loop optimizations. And basically, I get told all the time things that can't be done and do them anyway.
One from the internet is from Ricky. When is the backend getting a JIT and object file generation examples?
Why does it need a JIT?
I don't know. That's just the question.
I mean, you could use it as a JIT with some adaptation, but it doesn't actually need a JIT. So I guess I'm not quite understanding the question.
Yeah. Maybe you can ask on the forums.
Yeah, that was actually one of my questions as well. So there's been discussions on the forum of having a low latency JIT being used to optimize CTFE, and maybe even long term, which is to have an incremental build server. But that's of course a big thing. But have you given that a thought?
Okay, so the question is, why not turn CTFE using a JIT? The problem is CTFE works on the front-end data structures, not the really simplified back-end data structures. It would be really hard to generate code based on the front-end data structures, because there's a lot of simplification goes on to generate the back-end data structures. I suppose it could be done using the DMD thing. If you ran it through the thing that generates the intermediate code, and then you ran it through the JIT, I bet you could make that work, but it'd be a lot of work. So the good news is you wouldn't have to do the fix-ups or the horrible object file formats. The people who design those object file formats, I'd really like to sit down and talk to them and go, why are you why are you doing this? It's such a simple thing. Why does it have to be so complicated? I'll never understand it.
All right, well, I guess that's it. Thank you, Walter.